All right, hello my friends, welcome back. So today hopefully is going to be a shorter video than the previous ones because I want to have bite-sized chunks of zero knowledge learning. And what we're going to look at here today is a vulnerability that was published and discovered back in 2016. So this is an older vulnerability, but this is a good, I'd say, meta lesson for future vulnerabilities I'm sure that we'll discuss around zero knowledge. So this is specifically relating to Zcash, which is interesting because Zcash is pretty well known within the crypto ecosystem to be known as probably one of the most prominent and densely populated intellectuals around zero knowledge proofs, cryptography, etc. So in this vulnerability, it's called a internal H collision hash or collision vulnerability. And the reason that we're going to talk about this today is because I came across this blog post here and this GitHub thread right around here. And here you can see this is the blog post that was published. And Zcash did a great job walking through specifically what the vulnerability was, why it happened, the fix for it, and also kind of the major mistake that happened. It's very rare that you find a vulnerability, at least from what I've read through, where somebody actually explains in depth what happened in a succinct way that's actually understandable by the masses, which is part of the reason why I wanted to summarize this to you, because I actually understand it, at least I understand it more than I understand most things in zero knowledge. Because I, as I'm sure you, will quickly find out that there are certain parts of zero knowledge that are much more difficult to grok due to all the fun math. All right. The way that we're going to do this is we're going to walk through different sections. So we'll do impact, we will do the mistake, we'll do some kind of prerequisites to understanding the mistake in a deeper detail, and then we'll end with the fix. So that'll be the flow of the conversation. So first and foremost, the impact. So what is this vulnerability and what's the overall impact? So the overall impact here is actually the ability to double spend as a potential exploiter or attacker. And the way that this double spend can actually have a large impact is creating money out of thin air, but not just creating money out of thin air, but actually being able to double the wealth of the individual that's doing this attack. So that's kind of the impact here. Here's some quotes from the Zcash blog that kind of summarize what's happening here. First off, we can see that there's a 128-bit hash that is collision, not resistant, but there's an ability to collide those hashes within that hashing function. And that collision is what causes this ability to double spend. Down here you can see they walk through specifically kind of the use case as to how that could happen and have a big impact. And you can see they basically state that effectively they can double their wealth by combining all of their Zcash into a double spending note and then double spending that themselves. So if you take all your wealth and put it into this note, and then this note actually has, say, 2 hashes that collide, meaning that you can take this one, put it in here, take the money out that you already put in, but also you can take this hash here and then pull it from another note, which seemingly should be the same, but it's not. They can then take out that amount of money as well from here. And the interesting thing about hacks more broadly within zero knowledge is depending on the type of implementation and how I would say zero knowledge the protocol is, their ability to observe this hack when it's occurring is pretty hard, almost if not impossible. I think there are different ways to detect hacks that are occurring within a zero knowledge protocol today, but this has been a heavy discussion probably in the last, I'd say, 3 to 5 years, where people have talked about how there would be concerns if the hack occurred within a protocol that was completely zero knowledge. That means that there's a chance that they actually couldn't see the hack happening because you can't really see the amount of funds going back and forth within the protocol. So somebody could basically create tons and tons of money out of thin air and then, get away without anybody noticing. But I'm sure that's hopefully been somewhat solved. So real quick, here's a funny little photo that I found on the Googs. And here we have Homer Simpson, and he's double spending. So if you've not heard about the double spending problem, this is basically what happens. So Homer has $1, and he's like, yo, I got $1, this is great. So I'm going to go buy beer and donuts. But Homer doesn't realize that 1 plus 1 does not equal 1, but it actually equals 2. So Homer's going to go here, he's going to go to this guy and get a beer. I think that's the beer guy. And then he's going to go to Apu to get a donut. And he's going to spend the same dollar twice. And the issue here is that we have, Homer's son. I don't remember his name, but this guy, he's adding these and he says, okay, well, this doesn't make sense because 1 plus 1 does not equal 1. And I think that's a joke to the whiteboard meme that he has. So that's double spending, where you take the same amount of money and you spend it twice, but no one actually knows you've done that, or you at least get away with the process of spending the same amount of value twice within whatever protocol. And that's what's happening here with this collision issue. So that's the impact. That's what's happening that could potentially hurt or harm the other users within the protocol. So what is the mistake? What actually happened here? Well, there's a few things we need to understand before we actually understand the overall mistake. So the things we need to really grasp, first off, are these variables here. And these variables here are sitting inside of an overall thing called a note, which I think this is the old term for note, and I think the new term is called coin. Reason being is I've read through some of the white papers that have been provided that are linked in the blog, and I didn't really see any reference to note. And I've only seen references to coin, which actually encapsulates the variables here that we're talking about. So a coin or a note is a base object within Zcash. And this base object has a series of values that have a specific meaning for the protocol, and they're important for a variety of reasons. So what I've done is I've dug through the white paper as well as a series of blogs and a lot of Google searches and tried to summarize these in a way that I at least understand, and hopefully you'll understand as well. So what we're looking at here is first off APK. So APK here, it's basically the public key for the address. So there's, I think, ASK, which is the secret key, and then we have the public key. And this is very similar to any other Ethereum address, where you have your public key where people can send you funds, and then you have your secret key where you can then send funds to others or ignite different types of contracts by signing and advising that this is actually you doing what you want to do with this address. So that's the public key, the APK. The V here corresponds to the amount within the note. So this is corresponding to the value that you're sending. So say, I forgot, I think they're called Satoshis or Zcash. We'll call them Zcashers or Zcashins. The Zcashins are being sent with the amount of value, so you're stating how much you want to send. The P here is referring to a secret value that determines the coin's serial number. So there's some stuff we need to define here, right? So what is a serial number? Well, a serial number is defined within the white paper as a unique string associated to the coin, which is used to prevent double spending. So this is my quote. It's similar to, from my understanding, it's basically like a universally unique ID to that specific coin. So a serial number, you can think of basically a serial number on a box or on a piece of fruit or whatever else. That serial number is basically saying that this coin here, coin 1, cannot be spent more than once because it has a unique serial number connected to it. So this unique serial number is serial number 1, and then if we had coin 2, and then somebody tried to use serial number here on coin 2, that would prevent it because this is unique and it's only attached to this one. There should be a binding factor here, which we'll talk about in the future. So that's the other piece. So we've gone through APK, V, and P. So now we're going to do R. So R is a bit slightly still confusing to me, but from my understanding, it's basically just a random number that's used within the commitment process to randomize the commitment that's then published to the blockchain. So you can think of this as just a generated random number that helps provide some randomness within the overall commitment that's then put into the chain. And we'll talk more about what that means in a second. So these are the series of values that make up this base object. So the reason this is important to understand is because within the blog post itself, they walk through a series of points. And I hope that you can see this. So we'll just do a bunch of zooming in so you can actually see this. These are my notes from a separate notepad, but you can see basically what I was trying to grok my head around, where we have, oh no, what did I just do? I pushed the wrong button, internet. Wait a second. All right, that was scary. So here we go. We have the values inside of that note object that we talked about before. Remember the note? And then you can see right below that this sentence states that as part of the protocol, commitments to the notes are published to the blockchain. So here is the output from this, once it's run through a hash function, is a commitment. So the CM. So this commitment is published to the chain. So we can try to draw this out quickly just so I understand it and so do you. So we have our blockchain with our blocks that are, going over time. And what's happening is when we're not publishing the note itself, so we have our note or our coin, we're not publishing this to the chain because this might have some data that could leak the secrets or the things that we're trying to hide. So this is going to be run through some sort of function F, and then out of this function, will come CM, which is our commitment. And the commitment itself is what is then published to the chain. And this is going to have both a secret, I think it's, the hiding factor. So we'll talk about this in a second. So there's a hiding factor as well as a binding factor. So the hiding factor quickly basically states that we're trying to hide as much information about this thing as possible, so there's no knowledge shared. And then we have the binding factor, which is binding this commitment to this note. So we're trying to prevent double spending. That in a nutshell is what the whole commitment publishing piece is about. So next we have the actual hash function that gets run through all this stuff. So this is our hash function. And there's a series of SHA-256 compression functions, which you can see down here is basically an internal function inside of SHA-256 that compresses the data down. So we're going to take here our public key, we're going to smush that against the p value, which was the secret value that then helped create the serial number. That's then going to output this thing called internal H. So the reason this is circled red is because this is where the vulnerability lies. But before we talk about that, let's get through the rest of this process. So here you can see that we're smushing those together, and it's important to state that we have, important, looks like I'm a rabbit. So truncated to 128 bits. So we're truncating this to a certain size, and this is going to be key as well, because this is allowing us to actually do the collision piece. So once we've smushed these together and we've put them inside of this variable is then going to be smushed against the R, which is the random value that helps us create that randomness piece. And that's going to come out with a variable K. And then K is going to then be here. It's going to be smushed against this and this. So the V, remember, is going to be the value of the coin. And then 0 to 192 is fill in the blank, not sure. So this is going to be smushed together here through this function, and it's going to be output into this variable, which is our commitment that is then, remember, published to the chain. Now, that's the process. And after the process, there's a few things to highlight down here. So first, you can see in the statement that the vulnerability sits within that variable here that we stated. And that's stating that this vulnerability exists because the scheme is missing a binding property. So the binding property, that if there's no binding property, that means that there's a way to actually forge alternative values here that are not the same. And down here, we can see that they actually talk about that in a bit more detail, where you can actually have two different values for APK, your public address, and also P, which is the secret value that helps create the serial number. And here's an example of saying that you can have two pairs of this. So two pairs, you can have the authentic pair. So this is, say, the authentic pair. And then we can have a forged pair, which is the fake pair. But in the end, no matter what happens, the internal H value is going to be the same for both of these. And you can see that I stated this thing here just to remember for myself. This little black mark here next to APK and P, this little black mark here, I don't know if you can see because I'm doing black on black, that's labeled as prime. So that's just within the math world or cryptography world to discern the difference between one value and the next. Even though they're the same, they're slightly different. And since they have this exploit or this vulnerability, that allows them to actually break the binding factor, where you can actually put a alternative value here and here, run it through the hash function, get two internal H's that are identically the same, which allows you to double spend. So I hope that makes sense. I'm going to talk through some more of the binding pieces to help you understand more about like what that means and how it fits within the larger picture of, I would say, bullet proofs, which is a form of zero knowledge proofs, and also bullet proofs are, I think, a smaller subset of a larger set of zero knowledge proofs called range proofs. So that's what this is all about here. We can see that there are two pieces. So this is all pulled from a specific talk that Dan Bonet did that I thought was quite good. So I linked it here and you should check it out. So in this lecture, Dan talks through some of the main properties that create security within a commitment scheme. And a commitment scheme is kind of a part of a zero knowledge proof. So ZKP has let's say, a commitment scheme inside of it, or underneath it, or baked into it, however you want to talk about it. And within that, the binding and hiding properties are very important for security. Now, the binding piece, I found this example that I've discussed in previous videos, where I think is a pretty good explanation of how bulletproofs work, but also there's a binding factor inside of this. So here we have two chefs. So we have let's call this Tall Chef and Small Chef. So Tall Chef has a commitment, and this commitment's created and they hide it inside of this treasure chest. So the commitment they make is, let's say, the number 5. So they're saying, I'm going to commit myself to this number 5, and I'm going to put this inside of the box. So once I put it inside the box, I'm unable to open the box because I'm going to take this box and I'm going to ship it off to Short Chef and say, hey, I've committed to this thing. You don't know what it is that I've committed to, but I'm going to put it inside of the secure ecosystem or the secure box, so I'm unable to cheat and change the value I've already committed to. So Short Chef says, okay, cool, thanks. They're going to sit there and they're going to hold this box for a little while. You can say some time later. And after they've held this box for some period of time, they're going to get the key. And the key is being sent from Tall Chef to Short Chef or Small Chef. And this key is going to allow the Small Chef to unlock the box. Once they've unlocked the box, they can see that Tall Chef committed to the number 5. And they can validate this is true because they know that nobody's tampered with it because they've protected it themselves. And they receive the key from Tall Chef. And what's happening here, this is a really this is summarizing the two things that we've discussed. So the binding is directly speaking about how Tall Chef had to commit to number 5, and Tall Chef was unable to actually touch number 5 or adjust number 5 because Small Chef was protecting it. Another thing is the hiding property. So the hiding property was around him putting it into the box. So once he locked the box, it was hiding. So he locked it before he gave it to anybody or exposed it to anybody. So no one really knew what was inside of this before it was opened. And that's the hiding property. So we have hiding and binding. What was happening in the Zcash vulnerability was there was a binding property issue, which we discussed previously. Here's a more formal way of explaining some of this stuff that Dan Bonet talked through. I don't necessarily think I'll talk too much about this because it kind of summarizes everything I've just talked about, but in a more formal way. Yeah, I don't think I'm going to talk too much about this one just due to the fact that it's a summary of what's above. But if you are interested in hearing a more formal understanding of what's happening here and how this fits within the hiding and binding thing, I definitely recommend listening to the lecture that's linked above. So below this comes to hash collisions. So I'm sure many of you have come across hash collisions and you understand it, but for those that this might be slightly new to, a hash collision is simply you put something through a hashing function. So this is a simple diagram to explain this. So we have our hashing function here, and we're running things through this. When we run the different variables through this, it's going to come out to a finite structured field, and that field is then going to be slotted into an index sometimes. And we can see here that in this example we have Jim, Rick, Rose, and Zig. So Jim, Rick, and Rose, and Zig are all different values, so they should never connect to the same hash at the end. What you can see here is Rose and Zig, they've both ran through the hash function and they've both landed on 5, which means that there's a hash collision here. They're colliding into each other into the same value. And that's the premise of a hash function. There's a lot of links inside of my notes here, so if you go to any of these links, you can read more about those. But that's kind of the intuitive understanding of what's happening. So if we go down here a bit further, we can see some references from the blog post as well as a white paper that they referenced in the blog post. And in the summary, the blog post basically states that it's both theoretically and also practical for an attacker to target their weakness in the vulnerability they found. The reason that's true is because remember how we talked about there was a 128-bit truncation that happened in the first part of the internal H function that we ran through. Well, this 128-bit piece, this allows an attacker to use a certain amount of computational power to find a colliding hash with a valid hash, because the amount of computation to do this isn't necessarily practically impossible. So if you look at this quote here from one of the white papers that they referenced, a parallel collision is basically when you run a series of computers in parallel to create a colliding hash that hits with the valid hash. And in this paper, they talk through for a MD5 collision. So MD5 actually uses 128. I think it does. NTI 128. And in this parallel collision, they say if you run 3 $10 million custom machines in parallel, then there's a probability that, or high probability that you'll basically find a colliding hash within 21 days. Now, you can think, okay, $30 million, it's a lot of money. But like I stated before, if you can actually put all of your funds into a single account and use the same exact commitment or note to unlock the 2 different accounts, then you can take your 30 million spent on your computers, throw all that into an account 1, get all that money out, and then go to account 2 and then get another 30 million out, and then you've just doubled your 30 million to 60 million. And you can continually keep doing this over and over. And that is that's a pretty great ROI if you're getting basically 100% on your money. And that's why this is a concern, and that's why they highlighted this vulnerability. So if we keep going through here, I'm going to see if I missed anything. There's, like I said, there's a lot of great links in here. There's one here from Computer File that talks through what hash collisions are and how they are correlated to this weird analogy of pigeons and boxes. Yeah. Now let's go to the fix. So with the fix is actually quite simple. Simple but beautiful. So what they're going to do here is they're going to swap out the commitment scheme for something that has a stronger security binding factor. And there's a lot of trade-offs here that someone has to think through when they're making this decision. The reason being is the trade-off really comes down to the hiding factor. So in the old version, so they had an older version that was vulnerable. In the older version, they had a hiding factor that was statistically perfect. So you can see that stated here. So what's the difference between statistically perfect and computationally strong? Well, from their definition, a statistically perfect hiding factor basically means that it's almost theoretically impossible to actually figure out what's inside of this piece, so this hiding piece. And that means you can have the strongest computer that you would ever want, and there's a higher probability that you wouldn't actually be able to find out what's inside of here. On the other end, computationally strong hiding basically states that it is possible, but it's very, 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 very hard. And if anybody ever actually is able to crack this and find out what's being hidden in here, they'd have to also crack SHA-256. And they came to the assumption that if an attacker can crack this, then we have bigger problems on our hands than just them getting access to our hidden factors. That's the kind of the assumptions made inside of the decision that the engineers made here from back in 2016. And actually, that's another point is, like I said, this is in 2016, this vulnerability. Since then, I think they've had at least 5 major upgrades within Zcash. And those 5 major upgrades have completely changed some of the protocols we're using today. So a lot of what I'm saying here isn't necessarily relevant to that protocol, but it's just a lesson learned around hash collisions and how that fits within the zero-knowledge ecosystem. All right, so some other quotes from here. We can see that they've talked more about statistical hiding properties. This here was the updated commitment scheme. So you can ignore that piece, that's an error. But you can see they're using SHA-256 instead today. And they also included our 4 variables here, but they also added another variable here. To be honest, I'm not really sure what this means. I tried to research it, couldn't find an answer. But I'm hoping that it probably helps some way to increase the binding factor. And also using SHA-256 helps as well. All right. Yeah, and so this is basically a summary of what I've stated already. So we can bypass this. But if you want a quote around the blog post, they talk through that piece there. And with that being stated, that is everything. So internet, this segment of notes and all these resources will be put on GitHub as per usual. So I'll put it out there for everybody to have access to. And yeah, I'll see you next time.